to the translator uh, in terms of communicating what exceptions need to be preserved, what exceptions need to be precise and which ones don't. That's one of the challenges that transmitter in particular faced in their implementation. And it can really improve the flexibility of reordering code. And the last important point here, which I think would be obvious to many of you, but I think is worth making, is that this instruction set comes without any specific runtime or specific runtime semantics. And that's crucial if you really want to be able to write arbitrary software on top of this.
So there's no guarantees of safety then?
There's no guarantees of safety. This is not, any kind of safety guarantee is left to front-end compilers and code generators.
What are the multi-threaded primitives?
Yeah. So we have a set of simple synchronization primitives, and we're not trying to be particularly innovative in terms of providing high-level abstractions for threads at the moment. All we've done is provide mechanisms to do synchronization, mechanisms to manipulate the stack. We have a research project that's actually trying to do something much more ambitious, which is to provide a simple abstraction of control parallelism and data parallelism. Because I think that can actually provide tremendous information to translate to the translator. But that's, I think it's so sort of ill-defined at the moment that I'm not really going to go into it.
So, another way of saying that is there a memory model?
There is a memory model. It's no more high level than the memory model of a standard RISC architecture. It's a simple weakly ordered memory model. And think about it as essentially the kind of memory model you get with fence instructions. We're not trying, again, to be innovative in terms of providing some kind of sophisticated memory model at this level. What we're trying to do is do something that's simple enough that we believe it can be used for software because we've already been using it on current hardware. Other questions? So there are a couple of, so how do you evaluate a VISA like this? There are a couple of things that we did in the micro paper. One is to argue just qualitatively that the information content is enough to do sophisticated compiler analyses and transformations. And the compiler system we've built called LLVM, I think is a good proof by example of that. We have a number of very sophisticated language pointer analysis algorithms, code transformation algorithms, data transformation algorithms, and others, which just shows that the type information that's available is rich enough to support those kinds of techniques. So that's the first criterion that we looked at. The second one was code size, and what we found is that the virtual object code is roughly the same in size, plus or minus about 15%, as a fully stripped, optimized native binary for x86 and for Spark. So you're not really adding a lot of code size penalty for the extra information and for the SSA representation that we've used. And finally, the one thing that I think is worth pointing out is that there is a very small semantic gap in terms of the operations between the virtual instructions and the native instructions. And that's important because it lets programmers reason about the performance of their programs by looking at assembly code if they're interested. So those are sort of simple criteria to evaluate the instruction set design itself. The translation strategy is something I'd like to spend just one slide on because I think there's one issue here that is important to keep in mind. We do not believe that doing completely online translation, optimization, and code generation is effective for exactly the reason Mendel pointed out. It's slow. It's slow to do sophisticated compiler algorithms of any kind. And what we'd like to do is to try and make it possible to do offline code generation and optimization as much as possible. The difficulty is that you're trying to do this in a translator that lives, at least in the last two of my three models of deploying this, in a translator that lives below an operating system. So the translator doesn't know what system calls exist, even what devices exist, let alone what device drivers exist in this particular environment. And the way we get around that is by defining a very simple storage API that allows you to write out a string of bytes with some tag, or read back a string of bytes with some tag, or query whether it exists. And if the operating system chooses to support that, chooses to implement this API using whatever system calls and internals it needs to use, then the translator can use that to cache translated code offline, to cache profile information offline, even to cache optional pieces of the translator itself so that they don't have to be kept on chip in ROM if you're doing this as a process design. But if the operating system chooses not to implement it, or the user stomps on it, or it goes away in any way, there has to be a fallback strategy so the code will execute, and we fall back on online code generation in that case. So the goal here is to do offline code generation wherever possible, but fall back on online when necessary, using this storage API. And that's the translation strategy that we use for LLVM code. There are a bunch of processor design implications for this. In fact, I think in many ways this is one of the most interesting research directions that one can work on. And I'm doing some research on this with a couple of computer architects at Illinois, Sanjay Patel and Craig Zillis. I'm not going to go into that here, but if you're interested, please feel free to come by and talk afterwards. What I thought I would do in the rest of the talk is just focus on the software implications. So the compiler system that we've built using this code representation is what I call LLVM, low-level virtual machine. And I think it does something that, once you have the kind of representation that we have, what LLVM does is fairly obvious. Fairly obvious to someone who's thought about static and dynamic compilation. The basic idea is that you can have multiple compilers generate LLVA code, which from source programs, we give that to a link time optimization framework, which can now do interprocedural optimizations on across module boundaries using the information that's available in LLVA. So you have the ability to do high-level optimizations at link time. And then you can execute this code in several different ways. You can execute it by doing just-in-time translation, by doing static code generation, or any combination of those two. In either of those two cases, we have a path profiling system that tries to identify frequently executed paths in the executing code. We provide that to a runtime optimizer. And this runtime optimizer has both path information and instruction, the higher level instructions, which then would have to go through a just-in-time code generator to do further optimization. You can also imagine using this kind of system to build an offline re-optimizer. This is not something we've done, but it's relatively straightforward to do that. A re-optimizer that could do optimizations between executions of a program using profile information that you've gathered from previous runs. This achieves the goal that you mentioned earlier of trying to exploit end-user information about usage patterns, profiles, and so on, rather than leave profile information primarily to be extracted at development time, which is essentially the state of affairs today with static languages. One interesting issue is how you compile dynamically compiled languages like